Bairi.
Sir, ever.
I am Pijus Bairi, Assistant Professor of Department of IT, Haldia Institute of Technology. Today I am going to discuss about the AVL tree. That is the introduction to AVL tree. And today we will discuss these following topics. The first one is what is binary search tree. Next, disadvantage of binary search tree. How binary search tree can be improved. What is AVL tree? Next one is rotations in AVL tree, and the last one is how to create the AVL tree. Now, before discussing the AVL tree, first of all, we need to discuss something about the binary search tree, because the AVL tree is also a binary search tree, but it is one balanced binary search tree. Now, what is binary search tree? Binary search tree is basically one binary tree which has the following properties. What are the properties? The first property is the left subtree of a node contains only nodes with key lesser than the node's key. What does the first point say? Say for example, this is the binary search tree, and here 8 is the root node of the tree, right? And all the elements that belongs to the left subtree of 8 are lesser than the 8, right? Now what is the second point? The second point is the right subtree of a node contains only nodes with keys greater than the node's key. Here the root node is 8 and the entire right subtree of 8 contains the element or the key values, that is 10, 14 and 13. So all the elements at the right subtree of 8 are greater than the 8. And what is the third point? The third point is the left and the right subtree each must also be a binary search tree. That is 8 is the root node here, and the entire left subtree of 8 is this one, and the entire right subtree of 8 is this one. So all the elements at the left subtree of 8 are also a binary search tree, as well as the right subtree of 8 is also one binary search tree, right? So this is the binary search tree. That means we can say all the elements in the left subtree are lesser than the node, as well as the entire right subtree of the node is also greater than the node itself, right? Now where this binary search tree is used, basically the binary search tree is used to search the element in an efficient way. So it is useful for searching operation. Now how the searching operation is useful in or efficient in case of binary search tree? Say for example, for the given binary search tree, if we want to find the key element 4, then how we will perform the search operation? We are finding the key element 4. So while we are performing the searching operation of the key element 4, first we will compare it with the 8, and we are seeing that 4 is lesser than 8, so we will move to the left subtree of 8 only, because all the elements in the left subtree of 8 are lesser than the 8. So we are moving to the left subtree. Now the left subtree is headed by the node 3. Again we will compare the 4 with the root node, root node of the left subtree, that is 8, that is 3. So 4 is greater than 3, so we will move to the right subtree of 3, right? So in this way we are seeing that this is 6, so 6 is greater than 4, so we will move to the left subtree of 6, right? Now once we are moving that left subtree of 6, we are seeing that this is the element 4 that we want to search, right? So in this way we are performing the searching operation in case of binary search tree. Now how it is efficient? In this tree we are seeing that how many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are total 9 nodes are there in the tree. But while we are performing the searching operation of the key value 4, we need to compare, or how many comparisons we need to make. This is the first root node, 1, 2, 3 and then 4. So number of 4 comparisons are there to find the search element 4, right? Say for example, we want to search the key element 13, right? So how we will make the or how we will find the element 13 or performing the searching operation? We will compare the 13 with the root node 8. Then 13 is greater than 8, so we will move to the right subtree. In the right subtree, the next node is 10, so we will compare it with 10. As 13 is greater than 10, then again we will move to the right subtree. The right subtree is 14, right? Again we are comparing 13, so 13 is less than 14, so we will move to the left subtree of 14, and we are finding the key element 13, right? So in this way we can perform the search operation. Now if we make one, so all these are successful searching, that means both the key element 4 and 13 are present in this tree. Say for example, we want to 13 or we want to find the element 25. We want to find the element 25. So the first is we will compare 25 with 8. So 25 is greater than 8. Then move to the right subtree 10. So 25 is greater than 10. We will move to again to the right subtree. Right subtree is 14. So again we will move to right subtree of 14. Right. So we are seeing that the right subtree of 14 is null. So that key element 25 is not present in this tree. So this is one unsuccessful search. But if we find the number of comparisons, how many comparisons we have done? 1, 2 and 3. So by only comparing 3 elements, we can say that whether the element is present or not in this binary search tree, right? So if we find the number of comparisons, it always depends on the height of the tree. That means in this case, what is the height? Height is 1, 2, 3 and 4. So the maximum height of this tree is 4, and the number of comparisons is equal to the number of comparison is equal to the height of the binary search tree, right? So binary search tree is basically efficient way for searching an element, right? So we are seeing that the number of comparisons in case of binary search tree for finding one element is minimum is log n, that depends on the height of the tree, and the maximum height is n, right? Now what is the disadvantage of binary search tree? Disadvantage of binary search tree is that we cannot control the height of the binary search tree, right? So if we see some example of binary search tree, say for example, these are the given key values 25, 28, 13, 41, 17, 8 and 33. These are the different key values, and with these key values, if we create the binary search tree, how it will look like? So if we create a binary search tree with the following data elements, then how it will look? The first item is 25, so this is 25. The next element is what? 28. So 28 is greater than 25, so it will go to the right subtree of 25. That is, this is 28. Now the next element is what? 13. So 13 is less than 25, so it will go to the left subtree of 25. The next element is 41. So 41 is greater than 25, so we will move to the right subtree. Now in the right subtree there is one element 28. So with compared to 28, 41 is greater than 28. So again it will go to the right subtree of 28. Next element is 17. So 17 is less than 25. Then we will move to left subtree, and left subtree is headed by the node 13, and 17 is greater than 13, so it will be at the right subtree of 13. Next element is 8, so 8 is less than 25, then again less than 13, so it will move to the left subtree of 13. And the last element is 33. So 33 is greater than 25, 33 is greater than 28, and 33 is less than 41. So it will move to the left subtree of 41. So in this way, we can create the binary search tree. Now if we find the height of this tree, so what is the height of this tree? 1, 2, 3 and 4. So the maximum height of this tree is 4. So the searching operation will compare maximum or the minimum 4 number of elements, right? So the searching operation for this tree will be order of log n, right? Now we are taking the same key values but with a different order only. Now the order of the key elements are 41, 33, 28, 25, 17, then 13, then 8. That means we are taking the key values in a descending order. Now if we construct the binary search tree with this set of data elements, how it will look like? So the first item is 41. The next element is 33. So 33 is less than 41. So it will go to the left subtree of 41. Then the next element is 28. 28 is again less than 41, less than 33. So 28 will move to left subtree of 33. So in this way, it will be the next item is 25. The next key value is 17. Then it is 13. Then the last key value is 8. So we are seeing that all the elements are adding at the left subtree only, right? So if we find one element in this from this binary search tree, how many comparisons we need to make? We need to make the number of n comparisons, right? So in this case, the searching of a element is order of n, right? But all the key values are same as in the previous case. But in the previous case, the searching time for a BST was order of what? Order of log n. Order of log n. So order of n is much more greater than order of log n, right? So how this thing is happening? This thing is happening because of the height of the tree only. And we cannot control the height of the binary search tree. The height is only controlled depending on the order of the key value that we need to insert, right? So in this case, the minimum height is what? The minimum height of the tree is log n, and the maximum height of the tree is maximum height of the tree is n. So the searching time in case of BST ranges from order of log n to order of n. That is, the minimum time is order of log n and the maximum time is order of n, right? Now how we can improve the binary search tree? That means in case of binary search tree, we have seen that the minimum searching time is order of log n and maximum searching time is order of n. Now how can we improve the binary search tree? Now let us take one example. We have taken the three key values 35, 26 and 18. Now if we create the binary search tree with these following data items, how the tree will look like? The first one is 35. The next key value is 26, so it is less than 35. It will move to the left subtree of 35. Then 18. 18 again less than 35, less than 26, so it will move to the left subtree of 26. So the tree will look like this. Now we are taking the same key values with the different order. So what is the order? The first one is 35, then 18, then 26. So how the tree will look like? It is 35, then 18. So 18 is less than 35. It will move to the left subtree. Then the 26. 26 is less than 35. 26 is greater than 18. So 26 will be at the right subtree of 18. So the tree will look like this one. Next key value is 26, 18 and 35. So first one is 26, then 18. 18 is less than 26. So 18 will be at the left subtree, and next is 35. So 35 is greater than 26. So it will go to the right subtree of 26. Now the tree will look like this. The next data item are in order 26, 35 and then 18. So how the tree will look like? So it will look like 26, the next element is 35, so it is greater than 26, so it will be at the right subtree, and then 18. 18 is less than 26, so 18 will be at the left subtree of 26. So the tree will look like this, and the last two sequences are 18, 26 and 35. So how the tree will look like? First one is 18, then 26, it is greater than 18, and then 35. So 35 again greater than 26, so 35 will be at the right subtree. And the last sequence is 18, 35 and then 26. So it is 18, then 35, 35 will be at the right subtree, and 26. So 26 is greater than 18 and less than 35, so it will be at the left subtree of 35. So this is the tree that we have got, right? So how many trees we have got? We have got six binary search tree with the same data item, but their order is only different. Now if we compare these 6 figures, we will find that the first one is having height 3, this one is also having height 3, this one is also having height 3, and this one is also having height 3. But this one and this one, these two trees have height of 2, right? So if we decrease the height of the tree, or if we make the height of the tree as low as possible, then the searching time of an element will be low, right? So for these 6 binary search trees, this tree and this tree has the minimum searching time, but rest of the 4 trees take a larger searching time. Now if we can convert these 4 binary search tree having height 3 to convert it into a height 2, then it will be more efficient to search an element, right? Now can we do this binary search tree of height 3 to reduce to a height 2? Is it possible? Yes, it is possible. So we prefer the smallest height BST for the searching to be efficient, right? Now how we can reduce the height of a binary search tree? We can reduce the height of a binary search tree by rotating the different key elements, and from this we have got the idea of AVL tree. Now what is AVL tree? AVL tree is a non-empty binary tree. T is an AVL tree if and only if given TL and TR to be the left and right subtree of tree, and H of TL and H of TR be the heights of the subtree TL and TR respectively. and TL and TR are also AVL tree, and the difference between the height of the left subtree and the right subtree is less or equals to 1, right? So if we find the AVL tree, if we find the figure of this AVL tree, then we will see that this is basically one binary search tree, right? And why this is AVL tree? This tree is headed by the root node 12, and this is the entire left subtree of 12, and this is the right subtree of 12. Now, for this binary search tree to be an AVL tree, the height of the left subtree and the height of the right subtree, or the difference between the height of the left subtree and the height of the right subtree, must be equal to -1 or 0 or 1. These three values are permissible, right? That's why we have taken the mode of HTL minus HTR less or equals to 1. And this difference of left subtree and the right subtree is basically known as the balance factor. That means the value of the balance factor must be either -1 or 0 or 1. Then only the binary search tree will be an AVL tree, as well as the left subtree, that is TL, and the right subtree TR must also be an AVL tree, right? Now if the binary search tree is not maintaining the property of the AVL tree, then what should we do? We need to perform the rotation to make the tree balanced, right? That means if the balance factor is -1, 0 or 1 for each and every node of the tree, then we can say that the entire tree is balanced. But if the balance factor of any node is other than -1, 0 or 1, then the tree is not an balanced, right? So then in that case we need to perform the rotation. Now what are the different type of rotation that we can perform in case of AVL tree? In case of AVL tree, for an imbalanced binary search tree, we can perform the rotation to make the tree as AVL tree, and the rotations are LL rotation, LR rotation, RR rotation, and the RL rotation. These four types of rotation we can perform. Now among these four types of rotation, the LL rotation and the RR rotation are basically known as single rotation, and LR rotation and RL rotation are basically known as the double rotation. Now we need to find out what is LL rotation and what is RR rotation. Say for example, we have given three key values. Suppose the first key value is 15, then next key value is suppose 11, so it will go to the left subtree of 15, and the next key value is, say for example, 7. So 7 will also go to the left subtree of 11. Now if we find out the balance factor of that node, then what we will see? We will see the balance factor of 7 is what? 0, because the left subtree is null as well as the right subtree is null. The balance factor of 11 is what? It is 1, because the left subtree of 11, or the height of the left subtree of 11 is 1, but the height of the right subtree of 11 is 0. So 1 minus 0, that is 1. And the balance factor of 15 is what? It is 2. How? The left subtree of 15, the height of the left subtree of 15 is what? 2, and the height of the right subtree of 15 is what? 0. So 2 minus 0, this is equals to what? 2. So we are saying that the balance factor of 15 is 2, balance factor of 11 is 1, and the balance factor of 7 is 0. So this binary search tree contains a node having the balance factor 2, so the node is imbalanced, right? Now in this case we have seen that 7 is added to the left subtree, to the left of the left subtree of 15. The 7 is added to the left of left subtree of 15. That's why we need to perform the LL rotation, right? Now what is the LL rotation? LL rotation means we will rotate the tree in this direction, right? Now if we rotate the tree in this direction, then how it will look like? After rotation, it will look like this. 11 will be the root element, 15 will be the right subtree of 11, and 7 will become the left subtree of 11. Right? So now if we calculate the balance factor of this tree, we will find that the balance factor of this one is 0, balance factor of this one is also 0, and the balance factor of this one is also 0. That is 1 minus 1. Right? So the balance factor of each and every node is within 1, 0 and minus 1. So now it is balanced. The next rotation is RR rotation. Say for example, we have given the data items 10, then the next data item is suppose 15, so it will go to the right side of right subtree of 10, and the next data item is suppose 17. So 17 is greater than 15, so again it will move to the right side. So if we find out after inserting these three key values, if we find out the balance factor of this node, it is 0. The balance factor of this node is minus 1 because the left subtree of 15 is height of the left subtree of 15 is 0 and height of the right subtree of 15 is 1. So 0 minus 1, that is minus 1. And the balance factor of this node is what? It is also minus 2 because the left subtree of 10 is height of the left subtree of 10 is 0 and the height of the right subtree of 10 is 2. So 0 minus 2, that is equals to 2. So again we are finding that after inserting the node 17, this node, the root node 10 has the balance factor minus 2. That is, it is an imbalanced, this node becomes imbalanced. Now with respect to this node 10, where we have added the 17, we have added the 17 to the right subtree, to the right of the right subtree. That's why we need to perform the RR rotation. Right? We have added the right subtree of 10 and to the right subtree of 10 we have added 17 at the right. That's why we need to perform the RR rotation. Now RR rotation means what? We will rotate it in this direction. Right? So after performing the rotation, what it will look like? It will look like this one. So 15 will become the root node. Then at the left subtree 10 will be there, and at the right subtree 17 will be there. Now the balance factor of each and every node is 0, right? So now the tree becomes balanced. So these are the two rotations, LL and RR rotation. So these are the single rotation. Now what about the other rotation, LR and RL? They are the double rotation. That means we need to perform two rotations to make the tree balanced. Now take one example. Say for example, the data item is 15. The next key value that we want to insert is suppose 9, and the next data item that we want to insert is suppose 12. So 12 is less than 15. Then compare with 9. 12 is greater than 9. So 12 will be at the right subtree of 9. Right? Now after inserting the data item or the key value 12, what is the balance factor? Balance factor is 0. Here the balance factor is minus 1, and here the balance factor is what? Plus 2. Because the right subtree of 15 is null. So the tree becomes imbalanced. So 15 is the node which is imbalanced node, right? So we need to again perform the rotation. Now what type of rotation we will perform? In this case, we have added the 12 with respect to 15. We have added 12 to the left subtree and the right, or at the right of the left subtree. So we need to perform the LR rotation. We need to perform the LR rotation. Right? Now LR rotation means what? This is basically double rotation. First we will perform the RR rotation, including this at the right, at the left subtree of 15. That means we will perform the RR rotation to the left subtree of 15, and the second rotation is LL rotation. Now in case of LL rotation, we will consider the entire tree. Now first rotation is what? RR rotation, and it will be applicable only at the left subtree of the 15. So if we perform the RR rotation, then it will look like this. Then 15 will become the root node. Then at the left it will be 12, and at the left it will be 9. So after performing the first RR rotation, the tree will become this one, and then again we will perform the LL rotation. LL rotation means what? Now we will perform the rotation in this direction, right? So now it will look like this one. So 12 will become the root node. At the left subtree it will be 9, and then at the right subtree it will be 15. Now the tree become balanced, right? So the balance factor of this node is 0, this is also 0, and this is also 0. So the tree is now balanced, right? So LR rotation, while we are performing the, when we perform the LR rotation, it is clear. And when we perform the LR rotation, first we will perform the RR rotation to the subtree of the equivalent node, and then again we will perform the LL rotation to the entire tree to make it balanced, right? So this is the LR rotation, and the last one is the RL rotation. In case of RL rotation, say for example, we have taken the data item, suppose 13. Then the next key element that we want to insert is, suppose it is 11. Sorry. The next data item, say for example, it is 17. And then the next item that we want to insert is, suppose 14. So 14 will be at the left side of left subtree of 17 because it is less than 17, and 14 is greater than 13. So in this case, what is the balance factor of each and every node? It is 0, it is 1, and in this case it is minus 2 because the height of the left subtree of 13 is 0. So now the tree becomes imbalanced, as well as this node is imbalanced. So to make the tree balanced, we need to perform the RL rotation. Why RL? Because we have added 14 to the right subtree of 13 and to the left subtree of what? 17. That's why we need to perform the RL rotation. Right subtree of 13 and to the left of 17. That's why we are performing the RL rotation. Now RL rotation means what? First we will perform the LL rotation, then we will perform the RR rotation. Now while we are performing the LL rotation, the LL rotation is applicable to what? In this subtree, right? So if we perform the LL rotation, then the tree will become like this: 13, then it is 14, and then it is 17. Now we will perform the RR rotation in this tree. So after performing the RR rotation, the tree will look like this. So it will be 14, then at the left it will be 13, and at the right it will be 17. Now the balance factor of each and every node is what? 0. So the tree is now balanced. So we have learned about the different rotations of an AVL tree, that is LL, RR, RL and LR. Now we will create an AVL tree with the following set of data elements, right? The first data item is what? It is 43. So 43 is there. After 43 it is 21. So while we are inserting 21, 21 is less than 43. So it will go to the left subtree of 43, and after inserting 21 we need to calculate the balance factor. So what is the balance factor here? Balance factor is 1. In this case the balance factor is 0. So now the tree is perfectly balanced. So we can make the insertion of the next data item. So the next data item is what? 14. So 14 is less than 43. Then 14 is less than 21. So it will be at the left subtree of 21. Now after inserting the 14, what is the balance factor of the node? The balance factor of this node is 0. The balance factor of this node is what? The balance factor of this node is 1, and the balance factor of this node, the node 43, is what? It is 2. So now the tree becomes imbalanced, right? Now if the tree is imbalanced, then we need to make the tree balanced, then only we can perform the insertion, right? So what type of rotation we need to perform in this case? We need to perform the LL rotation, because we have added 14 to the left of left subtree of 43. That's why we need to perform the LL rotation. Now LL rotation means what? We will rotate it in this direction, right? So after performing the rotation, the tree will be 21 will become the root node. Then at the left it will be 14. At the right it will be what? 43. Now the balance factor of each and every node is what? 0, 0 and 0. Now it is perfectly balanced. Now once it is balanced, then we can perform the next insertion. So the next data item is what? 29. So 29 is greater than 21. Then we will move to the right subtree. 29 is less than 43. So 29 will be inserted in this place. After inserting 29, what is the balance factor? Balance factor is 0 here. Here the balance factor is what? Here the balance factor of this node is 1. Balance factor of this node is what? It is 1 minus 2, that is minus 1. And the balance factor of 14 is 0. So now the tree is perfectly balanced. The next data item is 36. So 36 is greater than 21. So at the right subtree, 36 is less than 43. So we'll move to the left subtree, and 36 is greater than 29. So 36 will be inserted here. 36 will be inserted here. After inserting 36, what is the balance factor? Balance factor is here 0. Balance factor of this node is what? Balance factor of this node is minus 1. Balance factor of this node is minus 1. Balance factor of this node is what? It is 2. Balance factor of this node is 2. Balance factor of this node is what? It is 1, 2, 3. That is 1 minus 3, that is equals to minus 2. That is equals to minus 2. And the balance factor of 14 is what? 0. Right? Now, in this case, after inserting 36, the two nodes become imbalanced. This node having the balance factor minus 2 and this node having the balance factor 2. So, we will consider the first node. That means from 36 we will move towards the root node, and the first node that we encounter with the balance factor other than minus 1, 0 or 1, this will be considered. So 43 is the first node where the balance factor is 2. Now with respect to 43, where we have added the 36 to the right of the left subtree of 43, to the right and to the left subtree of 43. That's why we need to perform the LR rotation. Now LR rotation means what? This first we will perform the RR rotation, then we will perform the LL rotation. So the RR rotation will be applicable only in the subtree, and LL rotation will be performed in the entire tree. So after performing the LR rotation, how the tree will look like? It will look like, first of all, it is 21, then here it is 14, here it will be 43, then 36, then it will be 29. So after performing the RR rotation, this is the tree. Now we need to perform the rotation, LL rotation with this entire subtree of 21. So now it will become 21, then it is 14, then it is 36, it is 29, and it is 43. So what is the balance factor? Balance factor here it is 0, it is also 0, it is also 0, it is -1, and it is 0. So now the tree is balanced. Now the tree is balanced, right? After this, we need to perform the insertion of what? 24. So where the 24 will be inserted? 24 is greater than 21, 24 is less than 36, then 24 is less than what? 24 is less than 29, so 24 will be inserted in this place, right? Now what is the balance factor here? After inserting 24, what is the balance factor? Balance factor of this node is 0. Balance factor of this node is what? It is 0. Balance factor of this node is +1. Balance factor of this node is what? It is 2 minus 1, that is equals to 1. That is equals to 1. And balance factor of this node is 0. Balance factor of 21 is what? 1 minus 1, 2, 3. That is equals to -2. 1 minus 3, that is equals to -2. So after inserting 24, the tree becomes what? The tree becomes imbalanced because the node 21 having the balance factor -2. So again we need to perform the rotation. Now what type of rotation we need to perform? So with respect to 21, where we have added 24? With respect to 21, we have added 24 to the left of right subtree. To the left of the right subtree of 21. That's why we need to perform the RL rotation. We need to perform the RL rotation. Now what is RL rotation? RL rotation means first LL rotation, then RR rotation. So LL rotation will be applicable where? Will be applicable to the subtree, right? That means it will look like, so the LL rotation will be applicable to the subtree of 21. That means we will rotate it in this direction, right? So the tree will look like this is 21, this is 14, this is 29, this is 24, then 36, and then 43. Now we will perform the RR rotation to the entire tree. So if we perform the RR rotation, means what? The 29 will become the root node. Then to the left, it will be what? 21. It will be 21. Then it will be 14. Then here it will be 36. Then it will be 43. Now, what will be the left subtree of 29? What is the left subtree of 29? The left subtree of 29 is 24. So 24 will become the right subtree of 21. So 24 will be here. Right? Now, after performing the two rotations, now the tree is what? What is the balance factor? The balance factor of this one is 0. Balance factor of this one is also 0. This is also 0. The balance factor of this one is also 0. It is -1 and it is 0. Now the tree is perfectly balanced. After this, the last element is what? 52 that we want to insert. Now 52, if we insert the 52, so where 52 will be inserted? The 52 will be inserted. It is greater than 29, greater than 36 and greater than 43. So 52 will be inserted in this place. Now after inserting 53, again the tree is what? The balance factor is here 0, balance factor is here -1, balance factor is what? -1, and the balance factor in this case it is -2, and the balance factor of this, the 29 is what? It is also, the balance factor of this one is also -1, right? And the left side tree will remain as it was. So again the tree is what? Imbalance because of the node 36, because its balance factor is -2. So with respect to 36, where we have added 52, we have added 52 to the right of right subtree of 36. So again we need to perform the RR rotation. Again we need to perform the RR rotation to make the tree balanced. So how the RR rotation will be performed? Basically the RR rotation is a single rotation, so we need to perform the single rotation in this subtree, right? So RR rotation means we will rotate in this direction. So after performing the RR rotation, the tree will look like this one: 29, then 21, then 14, is 24, then it will be 43, then it will be 36, and then it will be 52. So after performing the rotation, the balance factor of each and every node is what? This is also 0, 0, this is also 0, and this is also 0, 0, 0, and 0. So the tree is now perfectly balanced, right? So this is the process of creating an AVL tree with the following set of data items, and while we are performing the insertion of each and every node, first we need to check the balance factor of each and every node, and if the tree is balanced, then we will perform the rotation. What type of rotation we will perform? It will be decided by the position of the newly added node with respect to the imbalanced node, right? And basically we need to perform the 4 types of rotation: LL, RR, LR, and RL. So in this way we can create the AVL tree. Thank you.